Hello, my name is Saif. I'm a U3 student in McGill, and today I'm gonna be presenting to you my conclusions about the Node2vec research paper. So let's begin. To begin with, I would like to explain the motivation behind this research paper. So the idea is that real-world networks, such as social networks or biological networks, often require predictive tasks, such as node classification or link prediction. So traditionally, these features for these tasks are hand engineering, meaning they are time consuming, domain specific, and are not easily generalizable. So the key challenges behind this is that the networks are typically that have nodes in the same community or cluster, or nodes that share similar roles patterns in the network. Uh, uh, like pre-existing automated feature learning methods often fail to capture both patterns effectively. So how do we tackle this is by automatic feature extraction. So the idea is to eliminate manual domain specific feature engineering for network tasks and to preserve network neighborhoods to capture both local and higher order structures in the limited representation. And finally, to enable broad applicability, so ensured learned embeddings perform well across multiple tasks. So the research question here is to how can we learn low-dimensional continuous node representations that scale efficiently to large real-world graphs. As for our proposed approach, it will be accomplished by an adaptation of the skip-gram framework to networks, which will basically preserve our neighborhood through mapping each node to a low-dimensional embedding and maximizing the likelihood of predicting a node's neighbors within random walks. Then it is to define a flexible notion of neighborhood via second order random walk guided by two parameters. Our first parameter P, which is the return parameter that controls likelihood of backtracking to visited nodes, and our second parameter Q, which is our in-out parameter that balances breadth first versus depth first exploration. Also, we have scalable training, which is accomplished by neighborhood samples accomplished by random walks, which feed into an efficient stochastic gradient descent with negative sampling. Also, the runtime of this is very fast, which is O of V plus E. This shows that our algorithm supports real-world large graphs. Finally, our edge embedding is accomplished by extending node embeddings to link predictions by combining pairs of node vectors, enabling edge-level tasks. As for the key findings from this research paper is that Node2vec significantly outperforms baseline methods such as deep-walk and line on multi-label classifications and link prediction, with gains up to 26.7% for node classification and 12.6% for link prediction. Also, we have found that the ability to bias random walks via the P and Q parameters helped Node2vec capture both community-based and role-based patterns, leading to richer node embeddings. Also, we have found that it is scalable and robust due to it having efficient sampling and training, which allows Node2vec to scale to networks with millions of nodes, which demonstrates the resilience to incomplete and noisy network data. Finally, we have also shown that it has broad applicability, that the learned node embeddings can be easily extended to edge embeddings using simple binary operations, making Node2vec suitable for a wide range of network analysis tasks. In conclusion, we have found that Node2vec has flexible and robust embeddings, which is accomplished by integrating biased random walks with a skip-gram-like objective. So Node2vec successfully captures both community-level proximity and role-based structural similarities. It also improved predictive performance since consistent gains in multi-label classification and link prediction highlights were shown. Also, it has shown that it is scalable and has practical utility since the approach scales to graphs with millions of nodes, showing robustness to noisy edges and adapts seamlessly to edge-related tasks. As for the implications and significance, it eases the burden of manual feature engineering, enabling task-agnostic feature learning for complex networks, and it also demonstrates how biased exploration via parameter P and Q can systematically address both homophily and structural equivalences. Finally, as for the limitation, we have found a limitation for parameter tuning, since selecting the optimal values for P and Q can be non-trivial and may require labeled data or domain insights. For future work or potential that can be improved, it has potential shown in specialized networks, since extension to dynamic, homogeneous, or sound graphs could further generalize the methods. It has also shown more work for deeper architectures, since combining Node2vec with deep neural approaches could unlock additional gains in representation power. Thank you.